all again very much for inviting me to give these talks. So the aim of these series of talks will be to show that in the context of ADS-CFT, the physics of entanglement, or the constraints satisfied by the entanglement structure of states in the CFT, are powerful enough to sort of pin down gravitational dynamics in the bulk. And indeed, you can think of sort of bulk gravitational dynamics as emerging from the constraints satisfied by the entanglement structure of states in the CFT. Okay. So at the outset, let me clarify what the statement is. So the statement that we are going to try and prove in several steps is the following. Suppose you have some state in a CFT, in a holographic CFT, and you postulate that you have some bulk geometry which computes the entanglement entropies of all of the subregions in the CFT using the Ryuta-Koyanagi formula. Okay. Then we are going to argue that this bulk geometry has necessarily got to satisfy the Einstein's equations. Okay, and this will follow just from the fact that entanglement entropies, or the entanglement structure of the CFT states, have to satisfy some constraints, and these constraints, when you translate them into the bulk, end up giving you the Einstein's equations.
And
okay. Yeah.
If you specify a walled
That's right.
formula for the generalized Ryuta-Koyanagi,
right,
you will get
the generalized. That's right. That's right. Okay. Very good. So yes.
I'm sorry to be so ignorant. I know the JMS, whatever generalization to Ryuta-Koyanagi, where you keep the one loop corrections due to entanglement in the bulk.
Yeah.
What's the walled? There's a walled generalization. I know walled formula for entropy.
Yes.
So is there a walled generalization for entanglement?
Yes. Yes. So that. No. I mean, it's just the statement that if you have alpha prime corrections, so in other words, instead of just having the Einstein term in the gravitational Lagrangian, you include some higher curvature terms. Then correspondingly, the entanglement entropy functional changes. So that picks up.
You repeat Maldacena and left curvature, whatever.
Yes.
You get some corrections.
G dom.
That's right.
All right. Sorry. Yeah. G. You do what G taught us, and that's what you mean by walled.
Yeah.
Okay.
That's right.
I'm
So
just getting it right. Okay.
Dong and.
But you can do G plus Maldacena, JMS, whoever those are.
JLMS.
For the okay, sorry. For the one loop, at least corrections due to matter, bulk matter.
Right.
All of that. But then that's no longer Einstein. No, that wouldn't be good. Wait. Go ahead.
Right. So there are higher curvature corrections which change the entanglement entropy functional, and if you use that functional, then you get the Einstein equation in the bulk modified suitably with the higher curvature corrections. Okay. That was the comment. In addition to that, there are also quantum corrections, which you were referring to. These come in the form of bulk entanglement, or if you like, JLMS and so on. And you will see where all of those corrections come in. I won't talk so much about higher curvature corrections, but the quantum corrections you'll see. Okay.
Probably a semi-classic in a semi.
Yeah. That's right. Okay. Very good. So just before getting into the details, let me just make one remark, which is that you can think of this program as essentially a realization of Jacobson's ideas about the Einstein equation as emerging from space-time thermodynamics, but in somehow like a much more concrete, in the concrete context of the ADS-CFT correspondence. Okay. All right. So let's get into the details. So in yesterday's colloquium, I did sort of review the first step, the sort of the derivation of the linearized Einstein equation around ADS from entanglement in some detail, but I'll probably go through it a little bit again, because there are some new members in the audience and there are people at the ICTS. So let me just very briefly go through that right now.
So let me ask you one general question.
Yeah.
An important thing about thermodynamics is that entropy always increases.
Yeah.
That will play no role in your
That's right.
discussion, right?
That's right. That's it. The constraints that we will get are somehow different. They're like the first law of entanglement and generalizations thereof.
That's because Ryutakian doesn't really compute thermodynamic entropy, right?
Yeah, that's right. It's entanglement entropy.
Right. But if you try, if there was something to this Verlinde idea that it's actually entropy driving gravity,
Mm-hmm.
then entropy increase should be somehow playing a central role.
Yeah.
And that is not the spirit of it.
Not in this context. That's right. Yeah. Okay. So the first thing we'll sort of very briefly review is the derivation of the first order, or rather linearized Einstein equation around ADS. All right. So this was done a while back in a nice paper by Faulkner, Van Ramstong, and collaborators. So the basic idea is that in the CFT you consider states. So we wanna look at geometries which are close to ADS. So in the CFT you consider states which are close to the vacuum. So they're essentially the vacuum plus some small deformation around the vacuum. Okay, and so correspondingly, the bulk geometry has to be essentially ADS plus some small deformation around ADS. Okay, so the key point is that when you have deformations of this type, the entanglement entropy of subregions in the CFT satisfies a particular identity, which is called the first law. So this is what's called the first law of entanglement. Let me explain it a little bit. So on the left-hand side, we have the first order deformation of the entanglement entropy of some subregion R. I haven't specified what the subregion is yet, but this identity is true very generally. So this is the first order deformation of the entanglement entropy. And on the right-hand side, we have the first order deformation of the expectation value of the modular Hamiltonian. The modular Hamiltonian, if you're not familiar, is simply defined as minus the log of the density matrix reduced on the subregion R, where again the density matrix is. So in this case, so this modular Hamiltonian is the modular Hamiltonian of the original state, the undeformed state. So in the present context, it's just this guy here. Take the reduced density matrix of the vacuum on the subregion R, and then the log of that is the modular Hamiltonian.
This construction, of course, does not demand that you started with the pure state.
That's right.
So for instance, that deformation that you did there, you could define some rho of epsilon, which is the projection operator on 0,
yep,
plus some little bit of the density matrix.
Sure.
And so on. All
sure.
This will go through in that case as well.
Yeah, I think the first law doesn't hold in that case. There can be some additional contributions.
I see.
You're assuming you're perturbing around the vacuum.
Right now, I'm assuming that I'm perturbing around the vacuum.
Perturb around the projection operator on the vacuum plus some mixed.
Yeah, but it's still a perturbation around the vacuum density matrix.
Yeah.
And then it takes this form.
I mean,
Sure.
I mean, in general, this won't be true, right? Because there'll be one more term.
That's right. There's one more term, but that term vanishes because the trace of rho.
Exactly, to linear order
Yeah.
and so on.
Yeah, that's right.
So
That's right. Trace of rho is
yeah,
concerned.
exactly.
I see. So I'll ask you later.
Okay.
If you don't mind, can you prove us that?
Sure. The proof is pretty simple. So the entanglement entropy is that. Then if you take the first derivative of that, of the entanglement entropy, then you get 2 terms. This term is the one that I wrote. It's the change in the expectation of the modular Hamiltonian, because minus log of r is the modular Hamiltonian by definition. And then you get one more term, which is this one. But this term is proportional to delta r, trace of delta r. And because trace of rho, trace of rho is 1, if you normalize the density matrix, then this is the same thing as delta of trace of rho, which is 0. So,
I'm sorry to ask you a very dumb question, but if I take delta of kr, why doesn't the log go away?
Delta of kr, you mean this term here?
Sorry, that delta epsilon there
Yes.
was taking delta of kr, right?
No, it's not taking delta of kr.
So explain what delta epsilon
It's
is.
this term. It's this thing.
That's the definition of delta.
Yeah, that's right. So you take the original modular Hamiltonian, you look at its one-point function in this modified state, right? So this is delta rho. That's the definition of this object.
Okay, fair.
So here, why did you use a pure state thing?
Yeah. Okay. Coming back to that question, that's good. So good. So as long as your density matrix is normalized, I think the first law will be true.
You use rho square equal to rho or anything.
That's right. That's right. That's a fair
Of
point.
course, this is a reduced case.
Yeah. So I think that I think you could have for example, you could try to run this argument in more general states, but at least the argument that I'm going to present now is very specific to the vacuum, and you'll see where that enters. But the first law, you're right. The first law can.
No, I don't have any problem with the vacuum. I'm saying that to start with the mixed state, which is the the projection operator onto the vacuum.
Okay.
Plus this epsilon delta psi. So instead of that, you just use some epsilon.
Oh, I see. You want to consider more general deformations which don't
just
preserve
the
the.
deformation part, if that is mixed, if there's a problem, or even in general, if you are doing this around some mixed state to begin with, so let's say a density matrix to begin with, and you make a small deformation of the density matrix by a little density matrix.
Right.
Then why?
Yeah, this is still true. This is still true. I'm not sure how much of what I'm going to say next will follow, but we can keep track of that if you want.
So if you have, let's say, black holes, then if you look at the entanglement entropy of the whole right CFT, then to the leading order you get area of the black hole. Now using second law, if you assume the second law is valid for the area, then what does it say for the entanglement entropy?
What does what say for the entanglement entropy?
So if you look at the entanglement entropy of the whole of right CFT with the left CFT,
Yes.
that will be given by the area to the leading order.
Yes.
And now if you on top of it assume that the area increases under certain deformations, second law, then what does it say about the entanglement entropy?
So I'm not.
It's not around radius.
I understand, but I mean the first law in that case is the statement that the first order change in the entanglement entropy is the expectation, or is the same as the first order change in the energy, because in that case the modular Hamiltonian is the Hamiltonian.
I'm saying from the gravity side, if you assume the second law,
Yeah.
say you assume that, then what does it say about?
I mean it says that the entanglement entropy increases.
But it can't say that, right? Because if you do something just on the right,
That's right.
entanglement entropy won't
That's right.
increase.
So then you can't assume the second law in that case.
Yeah, these are different things.
Yeah.
The second law is about some coarse-grained entropy.
Right. That's right.
The entanglement entropy never increases if you just change the right.
That's exactly. You need some kind of open system dynamics for that. Yes?
Why is this called first law?
Because it's analogous to the thermodynamic first law. ds equals td.
Is equals d with some t set equal to
1.
2 pi in this case. Yeah.
I'm going to ask a very stupid question. The expectation of any operator in a density is just defined as trace of rho times that operator.
That's right.
So that very first definition of SE,
Yeah.
is that not already the expectation
Yes.
Okay. So the first law is just that SE is already equal to expectation of K. Is that?
No,
And
the
then
first law is this statement. Is the change, the first order change.
But then it seems with that definition, SE that you have, that's the definition.
Yeah.
But then the trace of, if you define the operator K as log of R,
Yeah.
that's also just the expectation of KR.
Yeah.
Okay.
But then at first order, when you take the first order deformation, you can get extra terms, right? For example, here you see this term. In this case, we were lucky enough that this term canceled out. When we do the second order calculation, we'll see that there are actually more terms.
I think Prahar was asking why isn't, if S is equal to K, why isn't that obvious?
Yeah.
And I think the answer is that the right hand side, the delta E is misleading.
It's not the variation.
It's not the variation of K, it's the variation, the original K in the.
That's right, that's right. So
that's what gives it content.
yeah. This is the definition of that. Okay, very good. So we've derived the first law in very great detail. Good. Now, so to derive the linearized Einstein equation around ADS, we want to specialize this. Well, first of all, we have the case of the vacuum in the CFT, or close to the vacuum. And secondly, we want to specialize this discussion to the case where we consider simply ball-shaped regions. Okay. So when R is a ball-shaped region in the vacuum of a CFT, the nice thing that happens is that this modular Hamiltonian becomes a nice sort of local integral of a local operator. In particular, it takes the form up to some overall constant, which I'm not going to worry about. Okay. So you can think of this statement here as the generalization of the statement that if you look at the modular Hamiltonian for a half space, then that's simply the boost operator restricted to the half space. Okay. This statement is more generally true in the vacuum of CFTs for ball-shaped regions, because any ball-shaped region is conformally equivalent to a half space. Okay, so you can derive this this statement. Psi of x is some vector field. So for example, if you had a half space, this is time, this is x1. For a half space, this psi is just the boost, one-sided boost. And for the case of a ball-shaped region, it's the analogous thing. But it's a conformal isometry in that case. You basically do a conformal transformation from flat space to get this psi of x. Okay, very good. So that's what simplifies life in this case of the ball-shaped regions. So now let's, having reviewed some of this background, let's come to a lightning derivation of the linearized Einstein equation around ADS.
In this conformal map,
yeah,
the boundary of the half space maps to the boundary of your ball.
That's right.
And this boost vector field vanishes
Vanishes on
at the boundary.
That's right.
So it's some vector field that is,
okay, good. So to derive the linearized Einstein equation, what one does is one uses the following gravitational identity. Okay, so this is what I'm going to write is a purely gravitational identity. It's the following statement. So for now, let me specialize around ADS and write this identity around ADS. Well, okay, let me not do that. Sorry.
What
Yeah.
was T hat O?
It's the stress tensor.
Why
The
why
0,
is
0
it-
component.
Why is
So think about the boost case. In the boost case, the boost operator is basically x1 times t naught naught, written on this Cauchy slice. So when it turns out that when you do this conformal transformation, that's all that happens. It's essentially more generally, you can think of this as this vector field dotted into the stress tensor, and then integrated with the time-like isometry, or the time translation vector field.
Sorry, a boost moves t proportional to x, but
Yeah.
also moves x proportional to t.
That's right.
Why isn't that second term?
Because you're evaluating at t equals 0.
Thank you.
It's special at that slice.
Yeah, yeah. It's special when when you write it on this slice, when you write it on R.
Okay, thank you.
Yeah. Good. So let me explain what this identity is saying. So what you have here is that you have your boundary space-time, and then in this boundary space-time, we pick some subregion R. This is the domain of dependence of R. And in the bulk corresponding to this subregion R, there is some Ryuta-Kainagi surface, which I'm going to call R tilde. Okay, so this is the minimal surface corresponding to this ball-shaped region R in the original ADS spacetime. Okay. Before that, I should explain what this gravitational identity means. This gravitational identity here is so first of all, omega here is the gravitational symplectic form, so the symplectic form is a 2 form, so it takes in 2 entries. The first entry here is basically the deformation of the metric with respect to the state deformation parameter, epsilon. The second entry here is some Lie derivative. So the x vector field can be anything you want. This identity is fairly general. But for our purposes, I'm going to pick this x to be a particular vector field. The special vector field is the one. So remember that what you do is you take this conformal isometry which exists in the boundary, and corresponding to that, there is an isometry of ADS which acts on this, which acts essentially like a boost in the sort of bulk, the domain of dependence of the bulk entanglement wedge. So you can think of it essentially like a boost. What this vector field?
There's a unique extension.
Yeah.
That's the thing.
Right. There's a unique isometry which does that. You should think of this isometry as generating modular flow in the bulk. Okay. This vector field psi was generating modular flow in the boundary. Corresponding to that, there is a nice vector field in the bulk which generates modular flow. Okay.
Sorry, I'm missing you. What is omega? It's a symplectic.
Right. So omega is the symplectic form density of Einstein gravity. So in other words, if I integrate this object on a constant time slice in the bulk, then I will get the symplectic 2 form of gravity. Okay.
By symplectic, you mean in terms of x and p?
Yeah. So if you had just ordinary classical mechanics, this would be dp wedge dq. Roughly in gravity, you can think of this as delta g wedge delta k, where k is the extrinsic curvature of the constant time slice. But yeah, that's the rough.
And epsilon here is any parameter?
Epsilon is the parameter of the state deformation. So remember that we were thinking of states of this form. So far, I haven't specialized to the case of the vacuum, but in a second, I'll take this to be the vacuum.
Right. But this identity works for any 1 parameter set of metrics?
Yeah, that's right. That's right.
And the input g of epsilon is the change in g as you change metric as you change the state? Oh, sorry, what I did this?
Yeah, so g epsilon is this family of metrics as you deform the state in the boundary.
Just as a bulk identity, you take any 1 parameter set of metrics labeled by epsilon,
That's right.
This is supposed to be true.
That's right. That's right.
And sorry, the second entry is the extrinsic curvature. Or what is the second entry in the symplectic form?
So okay, so the first, yeah.
Second entries, yeah.
Right, right. So it's a little bit, yeah. So the first entry, first of all, is where you're evaluating the symplectic form. Okay, so yeah, point and phase space, right? Now this is a two form, so I have to give you sort of two deformations to feed it, right? And these two are those two deformations. Is that okay? Yeah.
This I thought this
Okay, variations. These are the two variations that you have to feed into the symplectic form. Yeah.
I thought this identity only worked if this identity assumes that G epsilon satisfies bulk equations of motion.
That's right. So yeah.
G satisfies linear
No.
equations of motion.
No. It's actually more generally true. I'll come to that in a second. So all of that is contained in what I mean by epsilon.
And what was chi?
Yeah. So okay. Yeah. So on the first of all, the left-hand side I hope is clear by now. The right-hand side, all that I need to know about this term is that it's a total derivative. So chi is a space-time d-1 form. So this object here is a total derivative in space-time. Okay. And to Prahar's question, there's another term which is proportional, or inside it there are terms proportional to first of all the background equation of motion, and secondly the linearized equation of motion for the state deformation of the metric. Okay.
So inside d chi, presumably you would write G epsilon not comma but semicolon, right?
Sure. Sure.
By d epsilon is the one that is the variation that contracts with the chi x, and the
With,
x is the thinning vector field that contracts with the d.
Well, this d. Okay, so maybe this is confusing. This is a space-time exterior derivative.
That goes with the x.
Not necessarily. So if you write this object out, it's more complicated than that.
But x is
So yeah, so the space-time differential forms don't mix all that well with the phase-space differentials or differential forms.
And sorry, just and x can be anything.
X can be anything. Yeah. Any vector field in space-time.
In space.
That's right.
Not an isometry.
No. I'm going to specialize in a moment to this special isometry, but as written, this identity is very general. Okay. Good. So the reason, okay, so I hope this identity is clear by now. The point is that you take this identity and you specialize it in various ways. So first of all, you pick your base point in phase space, or the background metric around which.
This identity, is it roughly that the change in a field under a charge is omega inverse acting on that charge?
Right.
H chi dot is H commutator chi. Is that basically what's going on?
Yeah, I think that might be a good way of thinking about it. Basically,
Maybe I said wrong. A dot. See, there's something's happening here. There's a change under a vector field here.
Yeah.
That's the change generated by something.
Yeah. Right. So let me try to say the following. So this is a pure gauge
Exactly.
thing.
It's a diffeomorphism.
It's a diffeomorphism.
And there's a charge for that diffeomorphism somewhere.
Right. So roughly what this is saying is that, well, a pure gauge deformation of the metric should be symplectic. Should not have any symplectic structure, roughly. Okay. But what this identity is saying is that the symplectic product of this pure gauge diffeomorphism with anything else is essentially a boundary term up to the equations of motion.
Yeah. If you wrote it with ABs, I think.
ABs.
Sorry. Anyway, we can.
I think what you are saying is it should be a total derivative in phase space. This is not that. This is the total derivative in space time.
Yeah.
Total derivative. I was thinking that was like sort of this Hamilton-Jacobi kind of. I shouldn't be. I'll explain. I mean, this thing here is omega AB, omega lower AB.
Yes.
One term is the change because of x, and the second term is something general.
Yeah.
That something general appears also on the right hand side, so it's just going to cancel out, right?
Yeah.
So it's going to be omega AB, and the change respect to x is something. Now I'll inverse that omega.
Yeah, it looks like Hamilton's equation.
Hamilton's equation.
The AB index is still on chi. I think that's what Prahad is saying.
What?
Omega AB has, the AB indices on omega are still there on chi.
Yeah, that's what I'm saying.
That's right.
There's no.
D is
The D is a space-time.
It's like D.
No, D is whatever it is. But here there's some one form contracted with something. So this is also two form.
This is a phase space one form.
No.
Phase space one form.
Is that no? This is a space time phase space two form. Yeah.
D minus 1.
Yeah. Space time d minus 1.
D minus
That's
1
right.
form is space-time.
Wait, but if I cancel the chi, I cancel the dg by d epsilon, then I've got a free index then.
Yeah.
Then I can multiply both sides by omega inverse.
Yes.
So I do get an equation that tells me that the change
Yes.
is omega inverse times something.
Yes.
That something has to be the charge that generates it.
Yes. The special thing about this formula is that charge is a boundary term.
The charge is
That's the
okay,
point.
fine.
That it's a total space-time.
Fine.
Because this is a canonical transformation. It's that equation that you are saying evaluated on a very specific change, which is a very specific change is diffeomorphism, which is a canonical transformation.
I didn't understand that, but okay. Okay, so you say that basically it's general relativity, the charges are boundary things.
That's right.
Basically. Okay, fine.
Good.
Why is there a unique extension of this psi thing here on the boundary to the bulk? How do you do that?
Well, basically, you have a conformal isometry in the boundary that pulls to an isometry in the bulk, right?
Well, that requires saying that I'm only looking for that kind of extension which preserves the Pfefferman-Rehen.
No. It's an isometry in the bulk. I didn't say anything about coordinates.
Where was the isometry?
It's this bulk. It's this thing I call psi b.
Okay,
Yeah.
but in the first equation, you said x can be any vector.
Yeah. This
now
ident.
we're going to use
Yeah.
Good.
Yeah.
I'm just making sure.
Yeah.
Oh, okay. It's this rigid thing.
Yeah. So I'm
It's not
specializing.
logic, okay. Sorry.
I'm specializing x to right. So this identity is general. I'm now picking x to be this very special vector field. Okay, good. So the reason to do that is the following. When you do that, you notice that what you get from these boundary terms. First of all, remember that this is a space-time exterior a space-time total derivative. So you get so first of all, what you do is you take this.
I just one answer. Is that equation supposed to be obvious or it requires a derivation?
No. It requires derivation, obviously. So you have to. This was derived by Hollands and Wall. I guess I should have Hollands and Wall and maybe Wall and Iyer.
Two derivative gravity or is it more general?
This is, I think, more general for the class of Walled Lagrangians.
I think you can show that for any gauge transformation, it will always take this form. So diffeomorphisms or gauge theory will be this form. Now the explicit forms of omega and phi are also going to depend on which action you start with.
The fact that it's a gauge transformation was the statement that shows a canonical transformation. It does not change the symplectic structure. This is the reason it is an exact d of something. In this case, the gauge transformation is diffeomorphism.
But is there a constraint that action should depend only on curvature and polynomials in that?
Yeah. So this is true for this Walled class of Lagrangians. Yeah. Good. Okay. So what I was saying was you take this identity and you integrate this identity on the sort of bulk Cauchy slice, which is
I'm just trying to get my head around this.
Yeah.
If I apply this identity to the diffeomorphism d by dt around flat space, then I should get just ordinary Hamilton's equations.
Yeah.
And can you roughly explain how that works? What is this chi?
Yeah. So I think that what happens to the chi is that you get a boundary term. So remember that it depends on where you integrate it, but if I integrate
on just
flat space, then you'll get a boundary term from this asymptotic boundary, and I suspect that what that gives you is the Hamiltonian. If you put in the fact that the asymptotic boundary conditions and the metric gives the stress tensor.
Particular one form.
Yeah. Chi is a special one form. I haven't written down the expression for it here. Maybe I have it somewhere. But I mean, it's something you can write down pretty explicitly.
The alien formulation, the equations,
Time zero.
Yeah.
what is it?
So,
Whatever equation.
right.
Yeah.
I mean, for example, in this case, if I integrate this on this bulk entanglement wedge, which is the region between R, the boundary subregion R, and this minimal surface R tilde, then the boundary term you get from asymptotic infinity is precisely the modular Hamiltonian. So for when you integrate this object on this region here between R and R tilde, the boundary term from asymptotic infinity gives you what we called delta epsilon of k before, the change in the one-point function of the modular Hamiltonian. When you integrate it on R tilde, this gives you the first order change in the area of R tilde.
So in particular, this thing will tell you that if you take a small diffeomorphism, a small gauge transformation, then the Hamiltonian, the charge corresponding to that.
That's right.
Right, so that's the content, right? That's why I had to get over there.
That's right.
Okay, thank you.
Yeah. Good. Very good. So so then what you get from this term here in this gravitational identity is basically the difference between delta A over 4g Newton, which is the change in the entanglement entropy by assumption. So remember, we are assuming that this bulk spacetime computes entropies using the Ryuta-Kainagi formula. So this term gives you the first order change in the entanglement entropy. The boundary term from the asymptotic infinity gives you the first order change in the modular Hamiltonian. This term is 0 because the background metric that we are using is ADS. And I told you that I'm using this particular vector field, which is an isometry of ADS. So this object here is 0. Okay? So the symplectic flux term drops out in that case. And so what you get is you get an identity of the following nature. So what you get is something like this is proportional or equal to something involving the linearized Einstein equation around ADS. Okay? And a moment ago, or a few minutes ago, we discussed that from the CFT point of view, there's the first law of entanglement, which is also an identity which follows from the entanglement, the definition.
I'm sorry,
yeah.
you said this, I was spacing out. Chi was in the KR computing. Why was that?
Can you say that again?
Chi on the R was the boundary?
Yeah.
Why
So this is the boundary term you get from here, from R here.
Because this.
So you use the fact, so you have some boundary term here. You can calculate that using the fact that the asymptotic boundary condition on your metric is the stress tensor. So you get some expression involving the stress tensor, and that is precisely this object. Because remember that for ball-shaped regions in the vacuum, this modular Hamiltonian turns out is basically this object written in terms of the stress tensor, and that's exactly what you find.
Chi is that two form there?
That's right.
That two form is evaluated with LXG and what?
So this two form, or this object here, depends on this first order change of the metric and this vector field. So this vector field is now going to be xi b.
Roughly, this chi is the symplectic potential. If you want to do no other procedure in this formalism, then if you know symplectic potential, then how do you calculate charge? It's exactly this integration of chi is giving you roughly the charge. In that sense, this is the symplectic potential.
Symplectic potential is like P dq.
Yeah.
Yes, P dq is like the symplectic potential, Now, if
It's,
you
it's,
have
the
a
bound,
case theory,
it's the boundary term when you vary a Lagrangian, right?
yes, it's the boundary term when you vary a Lagrangian. Now, imagine that your Lagrangian has a gauge invariance, and you can also choose so if you make a gauge transformation, that can be also compensated by changing the symplectic potential.
Sorry, I don't know. So chi is a two form. It's not exactly a it's not the symplectic.
Good.
Chi is on phase space. It's a two form.
Yeah.
It's not the symplectic form. So the symplectic form is something else. I don't think he's written that. You take the exterior derivative
No,
of that.
d chi is a two form.
No, D is in space-time.
That's a space-time.
Chi
Oh,
dk, both of them
I
are
see.
two form. But
Excuse me.
chi is the one, exactly the one that goes in the formula for charge, right?
No, but as it says, but symplectic potentials are one form, right?
Yes, symplectic potential. So you can derive chi. If I give you the symplectic potential, you can given symplectic potential is a unique formula for deriving chi.
That's right.
It's a very simple change. It's an exterior derivative on the phase.
They're not exactly the same
I
thing.
just want
But
to say it's not the same.
they're not
Yeah,
exactly.
I
Of
agree.
course,
I
once
agree.
you give symplectic potential.
Chi is just
It's
something.
very much related to that.
Chi is just something that encodes the boundary terms. That's all.
Explicit formula for
Yeah,
it.
yeah.
Yes, yes. I'm sorry, I was just not saying that.
Omega is a D form, right?
In space-time, yes.
Space-time.
Yes.
Chi is a D minus 1 form.
In space-time.
In space-time.
Yes.
Omega and chi are both two forms in phase space.
Yes.
Okay. And this formula I'm understanding as an expression of ADS-CFT, right? Because if you've got a small change in the metric, that gives you a small change in the stress tensor.
Yeah.
It's integrated over a certain field.
Right.
That gives you a particular charge.
That's right. That's
So
right.
this is the formula I understand.
Yeah.
Now next formula here.
That's right. So here,
Why is
what you
that?
do is you evaluate the boundary term on R tilde, and you get some expression in terms of your delta G evaluated on R tilde, and you note that expression is precisely the first order change in the area of that surface.
And that sort of had to be true, right? I mean, this is basically how Wald derived
Yeah,
area.
that's right.
So
That's
that
right.
was guaranteed
Yeah.
to be true. Okay, fine.
If that Ryutakayana surface was not the extremal surface,
Yeah.
or some other one,
Yeah, then that would not be. I mean, then you would get extra terms from that.
why? I mean, would you still not get just variation of the area?
Um,
I'm saying, where did you use the fact that that was a particular Ryutakayana surface?
I mean, I'm not explicitly evaluating this for you, but if you do the computation explicitly,
But let's say
yeah.
my prescription was not the Ryutakayana prescription,
Mhm.
but if I were to say that the entanglement drop is given by some other surface, let's say,
Mhm.
you would still derive the equations of motion, Einstein equation of motion, right?
would I still derive the? Yeah, I'm not sure that this integral of chi on some arbitrary surface gives the first order change in its area. I mean, there can be some other contributions coming from non-extremality.
I mean, if it weren't an
Yeah.
extreme on.
Yeah.
I mean, that Ryutakayana surface also has some interesting properties which I now forget. Vis-a-vis its extrinsic curvature, right?
Its trace is
And
zero. The trace of the extrinsic curvature.
trace
That's the
actually.
extremality condition.
Okay, that's equivalent to
Yeah.
area. Yeah, so I think that probably.
That's what I was saying. Yeah, yeah.
Sounds right.
And what's the derivation of the lateral entropy? I think this is the extreme.
It's exactly, yeah, this is the same argument given in the context of Ryuta-Koyanagi surfaces, or entanglement entropy. That's right. That's right. That's exactly right. That's exactly right. So here it's the RT surface, which you can think of as the horizon of some hyperbolic black hole, and the boundary subregion R. Yeah.
Sorry,
Okay.
maybe why is I'm getting confused between what form is it in space-time and what. So omega is supposed to be the top form?
Omega is a D form, which is a
D form?
top form in space-time.
How do I see that? That it's a
Well, I haven't written out the explicit expressions, but if I did, then you would. So the point is that if you integrate this top form on a space-time, on a spatial slice, well, it's not a top form, but it's a codimension 1 form. So it's a D minus 1 form.
Okay.
So if I integrate it on a constant time slice, then that's what gives me the symplectic 2 form of gravity in phase space.
You have a symplectic current.
Yeah, that's a better word for this object.
Yeah, which you can then have to integrate, take the star of that and then integrate it over any space-like surface to get a symplectic form. That's the structure of this field.
Okay, so just to wrap up this discussion here, the first law of entanglement implies the left-hand side is 0. And so what you get is you get a family of constraints saying that these terms involving the linearized Einstein equation are 0. Actually, these terms here are all integrated on these sort of bulk entanglement wedges. But because this constraint is true for any ball-shaped region in the boundary CFT, you can show that essentially by taking derivatives with respect to the location of this ball and so on, you can show that this necessarily implies that the linearized Einstein equation has to be true.
Not just Einstein, but with higher curvature. Any
Right. So far, I'm restricting myself sort of to the Ryu-Takayanagi formula. If you try to do this with more general entanglement functionals,
but
then you would.
This identity is true.
Right.
With higher derivative gravity.
That's right.
Well.
That's right. So if you use the more general entanglement functional, then you would end up deriving the corresponding.
Where that equation of motion is integrated on a spatial slice, right?
So this term here is integrated on this sort of bulk entanglement wedge.
The whole space time, is it integrated over d dimensions or d minus 1?
D minus 1. So this slice over here.
Yes.
Okay, very good. So that yes.
So just on the CFT side, when you were evaluating this delta epsilon was a state deformation. So there was some psi that you were deforming. But on the bulk side, there was a metric deformation. So I think of that as a delta G mu nu.
Yeah.
What's the map between delta psi and delta G mu nu?
So think of delta psi as being a change in the stress tensor one-point function, being parametrized by the change in the stress tensor one-point function, and then it's the usual map.
And everything else. Only the 1 point, the stress tensor will matter.
Yeah.
Okay, can I ask you something?
Yeah.
Which is, Lefko, in a sense you could say this follows just from the basic arguments of Lefkovich and Maldacena also. This is a test of that, if you like. Because
Well, I would say Liukowitz-Maldacena goes in the opposite direction, which is you assume that the bulk equations of motion are true, and you derive Ryu-Takayanagi using a replica trick kind of argument.
yeah, actually that's what I was going to say.
But this is in the opposite direction, which is you assume Ryu-Takayanagi and you end up.
I see,
Yeah.
I see. Yeah, they assume equations of motion and then it follows.
That's right.
They say here you don't assume the equation of motion and then
And here you're allowing dynamics.
for any state you could have tried to use the replica trick. I don't know, you can try to think about that. Okay, you just, if you just run through that argument, they do use the equations of motion at various parts.
Sure.
Right?
Sure.
And so I'm just saying, in a sense, what you've done is, just to understand what you've done, you've taken two states separated a little bit. But if I were to just say, if Maldacena and Lefkovich were to have, if the replica trick were to work in both cases and give you the respective areas, you would be left with some remaining contributions in general, which are the equations of motion.
Yeah.
Right? And
So
that's
you could try to
very
play
close.
this game with
Right.
in the sort of Liukowitz-Maldacena setup as well.
In that sense,
That's
it's
right.
very close.
That's right. That's right. But I mean, I should emphasize that this was supposed to be just like a 5-minute review of
Yes.
of the work of
Rarely the case
some-
Nothing in the air.
yeah.
Don't take it as anything.
No. So I'm just trying to emphasize that this is not my work. This is like this is old work by Mark van Ramstonk and Tom Faulkner and collaborators. So I was just trying to review the fact that they showed
You'll
this.
find we're not familiar with the old world.
No, so that's okay. That's okay. I'm happy to discuss and so on. Good. So so that was the statement of their paper, which is that you can get sort of the linearized Einstein equation.
Now let me ask about the structure of this relation.
Yeah.
Of this. Suppose you take anything that transforms under the conformal group in the representation of linearized metric. Because conformal symmetry fixes its equation of motion, doesn't it?
Yeah. That's right.
So how could we have got anything else?
But
if we just keep conformal symmetry more or less.
yeah, no, that's a fair point. So then it raises the question whether we can generalize this to the nonlinear Einstein equation, right? So the linearized Einstein equation, as you rightly say, is more or less fixed by conformal isometries. The conformal.
So it's just a statement that you're working with a complete particular representation of the conformal group.
That's right.
the
That's
linearized
right.
Einstein equation.
That's right. I don't think I used that statement here anywhere. I was, we were.
Conformal invariance, right? Somehow.
That's right.
You use isometric. I mean,
Sure,
it's hard
sure.
sometimes to know what you've used.
Sure, exactly. So I completely agree. And so I think the right thing to do would be to try and see whether this logic generalizes to the nonlinear Einstein equation. And that's actually going to be the rest of the talk.
But if you have higher derivative gravity, you would still expect the same from conformal.
Up to a field redefinition, you will have to. You might work in some different choice of field, but in the end, the linearized Einstein equations, unless you have new poles, depends on what you do with your higher derivative. You take the derivatives very seriously, you might be generating many representations because you've got new poles. Most of them will be unphysical. They'll violate the unitarity.
And just to come back to this one thing, because in the back of my mind, I'm just thinking of Lefkovich, Malacena, etc., and the relation. In general, your deformed state will be time dependent.
Sure.
And so when you say
Well, I'm not sure what you mean by time-dependent state, because
well, I mean,
I'm
in general, epsilon delta psi will not preserve the time.
Oh yeah. That's right. Sure.
So it will be time
Sure.
dependent. So when you say RT, you mean HRT, I suppose.
Oh yeah, sure.
Yeah, so, but you can prove HRT also, I think. I haven't studied this.
That's right. There is a, that's right.
With not a very big twist on Lefkovich.
It's similar to Leukovic. That's right.
It's basically,
That's right. Okay, good. So so now let's try to take this. So the basic content of this paper here that I'm trying to talk about is trying to generalize this statement to higher orders. In particular, we showed that you can also derive the Einstein equation to second order around ADS using similar arguments. So let's go into the details of that. Okay. So first of all, if you want to do this to second order, as you would imagine, you want to expand. So the first law of entanglement was sort of the entanglement entropy expanded out to first order in the state deformation. If you want to do the second order thing, you better try and expand the entanglement entropy to second order.
Just to, sorry to keep
Yeah, no.
just to, if I were wanting to be an absolute purist or whatever, you can choose different regions in the boundary so that the residual equation of motion you're left with is any localized region.
So
you can do that.
that was the last step, which I sort of glossed over, which is that you take all your ball-shaped regions and you take derivatives and so on to get the
And just to understand the counting of that roughly.
Yeah.
As we discussed yesterday, that there are your ball-shaped regions are labeled by points in the ball, on the boundary, and size.
Right.
Which gives you as many roughly, which gives you more or less precisely as many points as in ADS.
Right.
But there is this issue of getting the indices.
Right.
Einstein's equations of d squared indices,
Right.
and I want to understand how you get all these d squared indices.
Right.
So I presume what you do is tilt your surface.
Yeah, you boost your surface.
You boost your surface.
Yeah, that's right.
But what confuses me a little bit is that seems to have d parameters, whereas you want to get d squared indices. So roughly, how does that work? I presume that it's a nonlinear thing. That you get d squared from d because there's something nonlinear. I mean, nonlinear boosts.
Right.
Not in reformation, but is that roughly right? You go to second
Right.
See, you want to get d squared equations.
Right.
Okay. Now, if you take one slice, you can get as many equations as points in space-time, but only one equation. So that's the information you have.
Right.
You need to get d squared equations. So now, but you don't take the same slice. You tilt your slices. That's boosting. If this was a linear operation, that would give you d parameters.
Right.
So it wouldn't be enough information to give you d squared equations. But because it's probably not a linear operation, you can go to quadratic order and boosts. I presume that's where you're getting your d squared from.
I think that's right, but I'm forgetting the details right now, so I'll have to get back to you on that. But I think what you're saying is at least morally correct.
Yeah, the counting seems to work because you want symmetric.
Right.
You want symmetric d squared.
Right.
Second order and boosts is symmetric.
Right.
And you know that there are actually one fewer equation than you think because of diffeomorphism variance.
Right.
And you're getting d squared in boundary.
Right.
So that seems to work.
That's right. Yeah, but I'm a little bit fuzzy on the details on that.
Okay.
But I'll.
You have different time slices on the boundary.
Right.
But knowing all the equations of motion on one slice does not ensure that the others are satisfied.
No, I mean not obviously, because these are different ball-shaped regions. You see, the equations of motion on one slice, you're not getting all equations of motion when you do on one slice. You're only getting one out of these. Just do the counting. How many balls do you have? As many as points in the bulk, but just one. One set of points in the bulk.
Yes.
So you do it on the slice, you get one cut in the equations of motion. In the index term. Now you do it in some other slide, you get some other cut. And the question would be, if you do it in all slices, you get all the cuts. And I think the simple way to prove it would be to just do the second order moves.
Yeah.
I suspect that's it.
Okay. Good. So okay. So what I was talking about here was the second order extension. Good. So at second order, if you try to expand the entanglement entropy, again, I'm going to restrict myself to ball-shaped regions because, as we discussed, that's where modular flow is nice and local and so on. Okay. So in this case, what you get is, well, first of all, you get a term which is similar.
Okay.
Yeah.
So now,
Sorry. For this modular Hamiltonian, that in the most general form would have had two vector fields contracted with T mu nu.
But that's not the.
That's the freedom of choosing different slices.
Right. I mean, so if you try to write the modular Hamiltonian on a general slice, you get a different vector field.
This
is the boost vector field.
Yes, and these vector fields are boost vectors. Therefore, taking it in all the slices is like taking all the indices. This is the intuition.
In the boundary, yeah.
In the boundary, modular.
But there is a very specific vector field that you're contracting into the stress tensor, which is the boost vector field. And the other one is the normal vector field on the Cauchy slice that you picked.
Yes, so given the normal on the boundary slice, you know exactly what K is.
Yes.
So
I mean, you can write K on that slice if you want.
Now if you change the surface, this normal will change.
Yes.
And that's the freedom, that if you change the normal, then you change one of the indices, but that is symmetry. Probably that is not working. This is the intuition.
I didn't follow the details. I'm just doing counting. I suspect that if you go to second order and boost, you have as many equations as you need, and then you probably get no more information going to the hierarchy.
Okay.
I sorry, before you.
Yeah.
Firstly, at the first order, because linearized matter does not source gravity, what the matter was doing was irrelevant.
Sure.
So now at second order,
Yeah,
what the matter is doing is going to be relevant.
It'll come into the.
Okay. So before you go, I just want to understand roughly what we know from general considerations. So everything is going to depend on the second order equations of motion, right? So third order Lagrangian.
Yes.
So we're looking at 3-point functions, basically.
Well, yeah, there's a sense in which you're looking at 3-point functions.
Okay. So any term in the Lagrangian that can affect 3-point functions, you should be sensitive to.
Yes.
Now the 3-point functions are parameterized by finite data.
Yes.
For instance, the 3-point functions here, will you be sensitive to the R cube? So the 3 graviton 3-point function
Yes.
has 3 structures.
Yes.
Will you be sensitive to all 3?
Yeah. So what you'll see is that I'm going to sort of specialize myself to CFTs which satisfy a particular constraint, which is the analog of the 4-dimensional C equals A constraint. So that's why what's going to end up happening is that you're going to get a particular 3-point function in the CFT, which is.
You will take all the. You will say the constraint is forcing you to take only the Einstein. But if you don't have the constraint,
Right.
then will you have all the 3 or not?
Well, it's a little bit tricky because if you don't have the constraint, then you have to change the entanglement functional.
Yes.
Yeah.
You definitely have to.
Yeah,
But
if you do
say
that,
this
then you.
parameter is by how many parameters? Two extra or
That's
one
right.
extra?
That's right. 2. So there are 3 in total, right?
3 in total.
Yeah.
So if you tell me that it is parameterized at 2 extra, then you have going through all of them.
Yeah,
Right.
So you do is understand how much we know from kinematics,
right.
and what the dynamics is.
Right.
So for the 3-point functions for the gravitons, we already know that it's up to 3 numbers.
Yes.
And then 3-point functions from graviton to, let's say, a scalar field, we know it's 1 number.
Yeah.
So there's a bunch of, for every field, there's a finite number of numbers.
Yes.
And you're going to pin down those numbers.
That's right. That's right.
And if you get exactly same number, then you are not gaining anything.
What do you mean?
You would have to give me the entropy functional. Say the entropy functional depends on n parameters, and kinematics tells you that there are n parameters, then you are not gaining anything.
If the entropy functional.
The group theory tells you how many structures you can have, let's say n. If the entropy functional that I should give you to get that same action, is it also n parameter, then you are not getting.
The gravity sector will definitely be also in parameters, right? Because each Lagrangian, there's a 1-to-1 map between.
That's right.
But maybe there's something non-trivial here in the sense about the matter.
Yeah.
Because the entropy functional doesn't know about the matter. But the matter part has to work out by itself.
Right. But okay, in a sense, you well, all,
It won't be as if,
Or it's not
if Ryu Takanagi is true, the matter will have to solve Einstein's equations correctly.
Yeah.
Regardless of the details. I thought that would be the general.
that's right. That's the kind of
So
statement
you
that
won't be
we're
able to pin down the matter couplings. I mean, the matter couplings will not be constrained. Yeah, it must
That
be
sounds
too much.
I mean,
Yeah.
Otherwise, replica trick would have to be wrong or whatever. Or the Ryu Takanagi function would have to be
No,
wrong.
in a sense, you'll see that the derivation will somehow use the universality of the 2-point function of the stress tensor. So,
universality of 2-point function.
yeah, the only additional sort of constraint which comes from the 3-point function is this C equals A kind of constraint, but you'll see where that enters the game.
Yeah. Waiting for it. But just again to get the context, just to understand how much is kinematics and how much is.
Right. No, that's a great question. Yeah.
Okay.
In a sense, this derivation is going to use the universality of the 2-point function. So it's a little bit unclear.
Okay,
yeah.
fine.
Sorry, getting back to this question, how is the entropy functional parameterized?
So if you have higher curvature corrections in your theory, then the entropy functional is not area over 4G. There are corrections that you have to include, which involve like higher powers of the extrinsic curvature integrated on the Ryu Takanagi. In that case, I'm not going to do that here. I'm just going to focus myself on the Einstein.
It's roughly the Wald formula with some corrections.
Yeah.
And at least the Wald formula, there's a 1-to-1 map between Wald formulas and Lagrange. So at that level, there will be no accomplishment. Because it's a map that's easy to invert. Right? Wald is derivative of Lagrangian with respect to curvature, you integrate. So, I mean, at that counting level, I don't think there'll be an accomplishment. It will be the conceptual stuff.
Right.
So given let's say you work with just the Einstein gravity, the corresponding Ryu Takanagi functional, and then from here you would see that the Einstein equations would you have to impose on top of that by hand A equals C, or A equals C would come out?
No, you have to, I'm going to impose A equals C, or the generalization of thereof. So that C equals A is the four-dimensional statement. There's an analogous statement in general dimensions, which I'm going to impose. Okay.
With matter, what you said?
I had first thought that we will learn something about the matter couplings, but then after Sandeep's comment, I realized that's too much to work for. I don't think we can learn too. Let's see, but I don't doubt you'll learn it. Yeah. I had hoped there was something new.
Well, at least one way it seems clear for any matter you can use the replica trick and get, if not Ryu-proof, if not Ryu Takanagi, whatever is the higher derivative. That's got to be true.
Right.
So you expect it to go the other way around.
That's right.
Just to ask again, if there is the kind of matter that has more than one coupling,
Yeah.
more than one structure, 3-point function of
Right.
It won't help us distinguish between them.
I don't think so. Yeah, that's right.
So
That's
that-
right.
that's
Yeah.
Another thing is that if there's massless matter, like there's some other gauge field or something, which you can't integrate, then how does it show up? I mean, you can't integrate that kind of matter. How does it show up in the Ryu Takanagi or whatever? Meaning that how would this show? How would this show up in the the area calculation?
If you have massless matter in the bulk.
I mean, if you by contrast, if you have massive matter, clearly you integrate it out, and you have some.
Integrate it out in that sense. I see.
Yeah.
But I don't think you need to integrate
Right, so
So
the matter back reacts on the geometry, that changes the RT surface and so on and so forth.
Exactly, exactly. You don't have to integrate it out for running the code.
Okay. Yeah, so coming back to this calculation, so at second order in this expansion, when you expand out the entanglement entropy to second order, what you get is, of course, you get this term which was also present at first order, but this is like the second order version of that, which is essentially that object there. This is more or less the definition of this term. In addition to that, you get an extra term now. So at first order, this was all. This was the first law of entanglement. But at second order, you get an extra term, which I'm going to write in the following way. What you can show that the second term is essentially the second order deformation of what's called the relative entropy, and the relative entropy is defined as follows. Okay.
But sorry, just to understand.
Yeah.
Rho is the full density.
Yes. So I'm being okay. So rho is the full deformed density matrix. So maybe I should put an epsilon on top of it.
Okay.
And delta 2 means keep the term that's epsilon.
Delta 2 means keep
the term which
order
is
epsilon squared terms.
Okay, got it.
Yeah, that's it.
Thank you.
Okay. So good. So now, if you want to make, okay. So okay. So that's the CFT part. I'll come back to this in a second. It's probably clear to you that if I have to make some comparison with gravity, then I need to be on top of what this term is. Okay. So that's going to be the bulk of the calculation. Okay. But just before we come to that, let's go back to this gravitational identity that we had from before and see what happens at second order. Okay. So at second order, what would happen is that first of all, there's this contribution here, but now because I have to keep track of up to second order terms, this piece which was 0 before, because remember x is this isometry, so it kills background ADS. But if you allow me to take a derivative of this term, then this is going to contribute. Okay, so at least from the gravity point of view, what happens is that you get this extra term in this identity involving the symplectic flux. Okay, and now so the point is that if you go through this analysis at second order, if this game of deriving Einstein's equations has to work, then you find that the symplectic flux term has got to precisely match with this relative entropy term. Okay, if that match worked, yeah. So yeah, so so at second order there's an extra contribution from this symplectic flux term, right? So remember that the boundary terms coming from here. What I'm saying is that the boundary terms coming from here exactly match, just like in the previous case, they exactly match these two terms. Then there's a term which involves the second order Einstein's equations, but now there is an extra term in the gravitational Ward identity. Okay, that extra term is non-zero at second order. Okay, and correspondingly on the CFT side, just to do the comparison between the two, correspondingly on the CFT side, there is an extra term which involves the second order relative entropy.
Would there be a second order term from dg by the epsilon?
Say which one?
The first.
Oh, this is 0 because then you would.
Next.
I think in Chi.
This one?
No, then he's already got second order from the first.
So what I'm saying is that the extra term from gravity is where I'm going to write this sort of translucently, where you put a derivative here, right? Because if I put the derivative over here, then this guy would give me 0. Does that make sense? Okay. So then the point is that somehow I have to show you that this second order relative entropy matches with that kind of symplectic flux.
And that is a bulk term.
So this is a purely CFT term.
CFT term, but there also, just to understand, the identity is true.
Yes,
So
but
you can always write the left-hand side as a boundary, space-time boundary, plus the equations of motion.
yes.
You're saying the space-time boundary term will have an extra piece, which is...
No, I'm saying that this term, the symplectic flux term, which is actually a bulk term, which is integrated on this slice in the bulk going between R and R tilde, integrated on the entanglement wedge in the bulk. So that's a bulk term, and somehow that bulk term has to match with this boundary term in this relative entropy term.
The first order, the left-hand side of this equation was 0, and
Yes.
the first term on the right-hand side gave you the first two terms.
Yes.
Delta S minus delta
Yes.
K.
Yes. Yes. Yes.
The Zyver equations of motion.
Yes.
Right. So here you're saying the d chi will give me the first two terms.
Yes.
But then what does Zy do?
What does this term? So
The last term I'm saying. You're saying this term should match the relative entropy term.
It's the equation, second order equation.
oh, this one. This one is proportional to the second order equations of motion.
It has to vanish.
So I want to argue that I get a constraint which says that the second order equations of motion vanish. Yeah. Okay, good. So let's then try to compute this object. So the way you go about doing that is the following. Okay, so maybe first let me write down a formula for this object, which is entirely written in the CFT. Oh, okay. I have to before I write the formula, I have to explain a few things. Yes. Yes.
So epsilon, the density matrix you're using here, is still the density matrix corresponding to the state, right?
This one?
Yeah. So here
Yeah.
the state is not being deformed to epsilon square order.
That's right. So in the state there are epsilon squared terms, but those don't enter the relative entropy. Those are all contained inside here. Yeah. So remember the definition of this object is trace with this delta 2, the second order derivative of the density matrix, and Kr in the original modular Hamiltonian. So all of those terms are inside of here.
I thought rho epsilon included epsilon square terms. Your relative entropy definition.
Oh, that's right. Yeah. No, you're right. You're right. So rho epsilon is the full thing, which includes up to epsilon squared terms. But so that's the definition of this object. But then I'm taking the second order derivative of that.
You're keeping the coefficient of
Yeah,
activity.
that's right.
So here the definition of psi is just vacuum plus.
Yeah. There is an epsilon squared term.
Yeah. So in the density matrix there will be delta 1,
What
delta 1
density matrix will have epsilon square with
with the vacuum.
Yeah, so vacuum plus first order correction in the state. If I make a density matrix out of it, that will have epsilon
That
square.
will have epsilon square.
But there will, or in it should be an explicit epsilon.
Explicit epsilon square.
So does this mean that from the bulk perspective, the metric fluctuation is also G is AdS plus epsilon H1 plus epsilon squared?
Right.
Where that
You're
epsilon
looking at
square
equations
H2.
for H2.
That's right. That's right.
And that
That's
H2 will receive contributions both from squaring the epsilon
Sure,
here and
sure.
The linear piece in epsilon.
Sure. Okay, good. Before we get to the relative entropy, I have to explain a few things about how we are going to proceed with this calculation.
It's incredible the such an identity.
Yeah,
It sounds like such an abstract thing in the field theory.
that's right.
That's so explicit in the first place.
That's right. Yeah, and it's actually, I'm going to argue that this identity is true in complete generality. In any CFT which satisfies this type of C equals A constraint, you can always show that the relative entropy has to satisfy this gravitational form. And that's just going to follow from the universality of two-point functions. Okay, so let's get into the details. So first of all, how are we going to do these various state deformations? So one thing is that so first of all, what we are going to do is we are going to use sort of the path integral formalism for generating states and density matrices in the CFT. Okay, so first thing to say is that the vacuum state in the CFT can be obtained by doing the Euclidean path integral on the lower half space. Okay, this is just the statement that that's roughly the vacuum. And so I can obtain the vacuum state by doing the path integral on the lower half space. Okay. Now the way so for our calculation, we need to deform our state in some way. The way we are going to deform the state is we are going to consider states which have sources turned on in this Euclidean path integral. Okay. So what that means is that the full action which is used in doing the path integral over here is the original CFT action plus some sources which are turned on. Okay, and these sources will in general be turned on away from the the Euclidean time equals 0 slice. Okay, so you turn on some sources down here in the path integral. Okay, so now if I want to get the density matrix, what I do is so remember what's the definition of the density matrix. So to get the density matrix, I have to consider the outer product of ket psi and bra psi, and then trace over R complement. Okay, so this is my ket psi. The bra psi is obtained by doing the Euclidean path integral on the upper half space. And remember that because this is the deformed state, there are some sources turned on in the path integral. So correspondingly, there will be some sources turned on here, which are basically, if this is lambda, then this is lambda star. Sorry? Yeah, that's right. Good. So that's the outer product of bra psi with ket psi. And then if I want to trace out my subregion R complement. So say this is R. Then what I do is along R complement, I glue these path integrals together. Oh.
Okay.
Okay. I don't know how far I should go with this.
We have 2 more lectures.
Okay, so maybe I'll just take I'll just take 2 minutes and finish what I was saying here. So the point is just that you glue these.
Start the early lectures and the next lectures.
Yeah. Sorry. So you just glue these path integrals together along R complement, and that's the density matrix. That's the sort of density matrix that's the path integral representation for the density matrix. Okay. And so the way we will expand this, maybe I should really do this in the next talk. But I'm just looking ahead. You can now take this density matrix, which remember depends on the sources that we turned on in the path integral. What we'll do next time is we'll expand in these sources. Okay, so when you expand in the sources, that's equivalent to sort of constructing the expansion for the density matrix in essentially this parameter epsilon that I discussed before. That when you do that, you pull down operators in this path integral, so you can write a pretty explicit expression for the density, how the density matrix looks in this expansion in epsilon in terms of these operators that will get pulled down. But okay, maybe I'll stop here and we'll continue from here next time.
Then you will get this formula for relative entropy.
Yeah, so first we'll get a formula for the density matrix, then we'll expand the relative entropy. That's a whole other set of things that you have to do there, and then we'll get some formula for the full relative entropy in terms of the 2-point functions of these operators, and then we'll take that formula, which is a purely CFT formula, we will rewrite it in the bulk in some way by using some tricks, and then do a few integrals, and then the gravitational expression with the symplectic flux will pop out of
That sounds incredible.
out of there.
But you do it perturbatively by pulling down factors of the operator?
Yes, yes, that's right. So that's why I was trying to introduce this formalism, because I have to do this expansion using perturbation theory.
And this is something that can be carried on order by order?
In principle, yes. To what extent this, so one thing that you will see helps you at this order is the universality of the 2-point functions in the CFT. That's going to enter this calculation in a crucial way. At higher orders, this is not true, but there's some higher derivative theory which can reproduce these 3-point functions. So maybe there's some way of doing this systematically. But
So Chirag was saying the relevant point function here should be the 3-point function, right? Or is it the 3-point function that is
so what you'll see next time is that in this calculation of the second order relative entropy, only the 2-point function enters.
But you also you have to use C equals A, right?
Yeah, I will have to use C equals A. And that's going to, okay.
Yeah, so what about the R cube term? Suppose I turn down an R cube term.
Yeah.
Does that affect C equals A? No, right? It's only the Gaussian effect. I want to know, the R cube term will affect your equation of motion.
there's one more left.
It will affect C equals A?
Yeah, I think so, right?
So, but still
But
there's
there's one degree of freedom. But maybe the fact that the 2-point function is not affected. Okay, so you could have Gauss 1A plus R cube. Yeah, so there's 1 degree of freedom. But the equation of motion will be affected independently by Gauss 1A and R cube. So,
In how many dimensions?
let's say 5 and I.
And just to understand, the Ryu-Takenagi surface with R cube and all has a generalization which Shi, Dong and so on have worked.
Sure.
So your question is, okay, we use that and we assume that and we want to derive the equations of motion. Will it go through with the R cube?
It sounds like he's saying that if you know that the 2-point function works and C equals A works, you will get Einstein's equations. That sounds funny to both Abhijit and myself, because there were 3 possible.
And the Ryu-Takenagi formula works.
And the Ryu-Takenagi.
Okay.
What's true in general is that the relative entropy can be written as a symplectic flux in the bulk.
But are you saying if you assume Ryu-Takenagi's generalization for the C not equal to A case, you run into a contradiction, or you
No.
done it?
No. So what we have done is that in the general case, we have run this argument, but not with the Ryu-Takenagi formula, with the more general high derivative corrections included in the Ryu-Takenagi formula.
But still
And
assuming C equals A.
no, not assuming C.
Okay.
Well, yeah, that was the point of doing the higher curvature.
And it goes through.
Yeah.
Okay, I thought you said you needed C equal to.
No, I need C equals A only for the Einstein equation
Only
to
for the
work out.
Einstein.
And the entanglement functional is the Ryu-Takenagi formula.
But it seems like an overkill to assume both C equals A and Ryu-Takenagi.
Uh,
Because Ryu-Takenagi should tell you that C was equal to A, right?
Yeah, so okay. So what happens is that
Which entropy formula?
That's what I'm-
That
Oh,
has the
oh.
information.
So
Ryu-Takenagi
Ryu-Takenagi is the area over 4 G Newton.
Now I understand what is it. Yeah, but that should
So
happen.
that is isolated Einstein gravity already, so you should see that only, right? So in other words, this would, out of 3-dimensional space of parameters, only one should have
Yeah,
been
so
chosen.
let me be clear. So what we will show is that this relative entropy term can be written as a bulk expression of involving the symplectic form, which I've erased, provided C equals A. And then the symplectic flux is that of the Einstein gravity theory.
And you're using Ryuta-Kanagi in that statement somehow?
No, the relative entropy equals bulk symplectic flux does not use Ryuta-Kanagi.
Just one.
Actually, I'm going to make it.
Okay, thank you for a very